Welcome to this lecture series in linear algebra. In this lecture, we'll discuss something very important, but it will apply to only upper triangulable operators, meaning upper triangulable endomorphisms. And therefore, they will apply to, let's say, any endomorphism on a complex vector space, because every endomorphism on a complex vector space is upper triangulable. So there is so much to recall. Some 6 facts, at least these 6 facts are needed. But in the interest of time, let me not go over every one of them. Let me ask you to just read them out for yourself, and I will just read out this one. So we have previously shown that if we have an upper triangulable endomorphism and we have a basis which witnesses the upper triangulability of the endomorphism, then the entries on the diagonal of this matrix are precisely the eigenvalues of the endomorphism. We will strengthen this fact today, right? So that will be sort of the goal of this lecture. And this is a very, very concrete thing that we are going to do. All these concepts that we have developed, all these, eigenpolynomials or generalized eigenvectors, they may seem like some abstract things. But what we are going to do today is very, very down to earth. Okay. Here are some problems for practice. This problem is sort of related to what we are going to do today, but it is nonetheless instructive. All right. So let's get started. And just give me 1 second. Right. So suppose T is some endomorphism which is upper triangulable, then every eigenpolynomial of T has degree 1. This is what we want to do, but this should be immediate. So first of all, we know that an endomorphism is upper triangulable if and only if the minimal polynomial splits. So the minimal polynomial splits over the base field. Therefore, the only monic irreducible factors of the minimal polynomial are of degree 1. Every monic irreducible factor of the minimal polynomial has degree 1. But we also know that the eigenpolynomials of any endomorphism are precisely the monic irreducible factors of the minimal polynomial. And that finishes the proof. That's it. So this is something that could have been left as an exercise, but anyway. All right. So here is one important lemma. Fix an endomorphism and suppose lambda is an eigenvalue of the endomorphism. Suppose we have some eigenvector corresponding to lambda and define the subspace U as the span of this eigenvector. Then clearly this is T invariant, and we may consider the endomorphism induced on the quotient space. Okay. So then the algebraic multiplicity of lambda with respect to T is at least the algebraic multiplicity of lambda with respect to T bar plus 1. Okay, so let's prove this. So we will make this arrow just for convenience, not going to help us with the proof or anything, but let us just make this arrow. Okay, so now we know that by something that has been written in the recall, we know that the dimension of the pullback of the space of all the generalized eigenvectors of T bar corresponding to lambda, which is nothing but this space, this dimension is one dimension of U plus dimension of the kernel above. Best to just copy it. Right? This is what we know. This we proved in a lecture not so long ago. and this was also written in the recall in the beginning. So dimension of U is 1, and this is nothing but the algebraic multiplicity of lambda with respect to T bar. Okay. And now we have the following claim, which will finish the proof. The claim is this pullback is contained in which is nothing but the space of all the generalized eigenvectors corresponding to lambda. And the dimension of this space is, of course, the algebraic multiplicity of lambda. And once we establish this from the previous equation, our result is immediate. So all we need to do is prove this claim. So it's very simple. Just start with something on the left-hand side. And just show that it is on the right-hand side. But if V is here, then it just means that pi of V is here. Which means if we apply this endomorphism, so just apply this endomorphism to pi of V. But what is pi of V? Pi of V is just the coset of V corresponding to the vector V. And we get 0. And this 0 is the 0 of the quotient space, and hence we write it this way. It is 0 of the parent space plus the vector space or subspace U. So this is the coset of 0 corresponding to, this is the coset of 0 in the quotient space. So we have this equation. This is the 0 of the quotient space. Okay, which just by definition gives us, and this is, or maybe let me just write one more step. This and a bar above V plus U. So this shouldn't cause any confusion. All I'm saying is that this endomorphism on the quotient space is same as first you consider this endomorphism on the parent space and then put a bar above, meaning then take the corresponding endomorphism induced on the quotient. And we have commented earlier that these two things are the same thing. You can just verify it by hand in real time if you're not convinced. So this is equal to that, and now by definition of the induced endomorphism, this just becomes this just means that this is equal to 0 plus U, which means this guy is in U, right? That's how quotient spaces behave. And if something is in U, it is scaled by T minus lambda I. So we apply T minus lambda I to it to get 0. Which is exactly the same thing as saying that, let me write here, it is exactly the same thing as saying that this is 0. Why? Because the dimension of U is 1. So this is dimension V minus 1, but we get a plus 1 because of this guy. And hence this equation is just this equation, which is to say that V is here. And that's all. This containment was the reduced goal, and we have proven this lemma. Okay, so now we can continue and prove the final result of this lecture. So fix an endomorphism which is upper triangulable, and once it is upper triangulable, the only eigenpolynomials are degree 1, and hence basically they are just eigenvalues. So let these be all the distinct eigenvalues of T, and let D be a basis of V which witnesses the upper triangulability of T, meaning that the matrix of T corresponding to this basis is upper triangular. Then the number of times a given eigenvalue appears on the diagonal of this matrix is same as the algebraic multiplicity of lambda I. So, as we recalled in the beginning, the entries on the diagonal are precisely the eigenvalues. But this theorem tells us more. It tells us how many times an eigenvalue appears on the diagonal. Precisely this many times. So the notion of algebraic multiplicity has a very matrix theoretic interpretation when you have upper triangulability. And hence on complex vector spaces, this theorem is very, very relevant. All right, so let's prove this. We will prove this by induction on n. What is n? N is the dimension of the vector space. So let me write the first line. We'll prove this by induction. Induction on the dimension of the vector space. Basically, we have done this kind of argument many times. This is the use of the well-ordering principle. So let n be the dimension of V and assume, and even before I write that, clearly the theorem holds if the dimension of V is 1. So for one-dimensional vector spaces, this is a very, very simple exercise. And now, so let dimension V equals n, which is at least 2, and assume the theorem holds for vector spaces of smaller dimension. Okay, so we just now need to prove it for this vector space V, whose dimension is n, and that will finish the proof. Obviously, so far nothing has been done. Okay, so now we start basically. So let B be a basis of V such that the matrix of T with respect to B is upper triangulable. The matrix is upper triangular, and we may say the matrix looks like this. So on the diagonals, we will see some numbers which we denote by mu1 up to mu(n), and above the diagonal something, below the diagonal all are 0. So say the matrix looks like this. Okay, and say the basis B is V1 up to Vn. So yeah, so the diagonal entries are obviously, as we said, are just these members. Some of them repeat some number of times. So we are not writing lambda 1, lambda 2 here. We are just saying it's mu1 up to mu(n), and each mu I is one of these people. Okay, and yeah, so say the basis is this, and therefore thus Tv1 is mu1 v1, and without loss of generality, we may assume that mu1 is actually lambda 1. We may assume that this guy is actually lambda 1. All we are doing is, if it is not lambda 1, just change the names and call mu1 lambda 1. So this is not cheating. Okay, so this is lambda 1 v1. So just to document that, mu1 is lambda 1 without loss of generality. Okay, so v1 is an eigenvector, and say U is the span of v1. All right, and yeah, before I write that, maybe I should mention something else. So let's say lambda I appears ki times on the diagonal of this above matrix, on the diagonal of this matrix. What do we want to do? We want to show that the algebraic multiplicity of lambda I is ki. So this is our goal. Okay. So just give me 1 second. Yeah. So let's say capital U is the span of V1, and since U is T invariant, by virtue of the fact that V1 is an eigenvector, we consider the induced endomorphism on the quotient space. U is a T invariant subspace, and hence we may consider the induced endomorphism on the quotient. So then it is a simple check. That this list is a basis of the quotient space, where of course V2 bar just means the coset of U corresponding to V2 and so on. So this will be a basis of V mod U. Just make a simple check, and let's say, or not let's say, and then observe, in fact, the matrix of T bar with respect to this basis looks like this. So on the diagonal, we will see mu2 up to mu n. Okay. So so above the diagonal there is star, and below the diagonal 0. So something appears above the diagonal. We don't really care. So the point is, the number of times lambda 1 appears here is 1 less than the number of times lambda 1 appears here. So the number of times lambda 1 appears here is k1 minus 1. And for every other eigenvalue, the eigenvalue appears here the same number of times as it appears here. So that is crucial. All right. So now, since T bar is also an upper triangulable endomorphism on a vector space of dimension smaller than V, by induction we have, this is a crucial step, so by induction we have that the algebraic multiplicity of lambda I, so for lambda 1, it is the number of times lambda 1 appears on the diagonal, which is 1 less than k1, and lambda I, this is k2 for all I greater than equal to 2. Okay, so we have that, and therefore the algebraic multiplicity of lambda I with respect to T is at least this much. So hopefully I wrote that in the recall. This is what we proved in the previous lecture, I think. So let me just recall, go to the recall and see if I actually wrote this. Yeah, I wrote that. So this fact. So we have that the algebraic multiplicity of lambda I with respect to the original endomorphism is at least that much, which is equal to ki for all I greater than equal to 2, right? And by the previous lemma, in case of lambda 1, this thing is at least the algebraic multiplicity of lambda 1 plus 1. right? Which is equal to k1 minus 1 plus 1, which is equal to k1. So collecting both these inferences in one line, all we are saying is that this exceeds kj for all j, which implies if you sum up everything, so if we sum up over all the eigenvalues, we get this, right? But what is this number? This is sum of the number of times lambda 1 appears on this diagonal, then lambda 2 and lambda 3 and so on. But there are a total of n entries, meaning dimension of v entries on the diagonal. And therefore the sum of k1 up to kn, k1 up to kr is has to be the dimension of the vector space. This is n, which is nothing but the dimension. And what about this guy? So we proved earlier that the sum of the algebraic multiplicities of all the eigenpolynomials corresponding to any operator, meaning any endomorphism, is equal to the dimension of the vector space. Now, since our endomorphism is upper triangular, upper triangulable, the only eigenpolynomials are the degree 1 ones, which are nothing but the ones corresponding to eigenvalues, and hence this sum is nothing but the dimension of the vector space. So this is equal to the dimension of V. Crucial point. So this is a sandwich. Left hand side and extreme left and extreme right are the same, while there's an inequality here. So it just means that all of these inequalities must actually be equalities. And this concludes that the algebraic multiplicities are actually equal to the number of times the corresponding eigenvalue appears on the diagonal. And this finishes the proof. So that is the proof of this theorem. Very nice proof. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.